So we are now in part 2 of chapter 4, and we will discuss power and energy and the relationship between work, power, and energy. So just to revisit our objectives, especially today, we'll be defining energy, specifically kinetic energy, gravitational potential energy, strain energy, and explaining the relationship between mechanical work and energy, and then we will also discuss and define power. So energy is defined as the capacity to do work, and it comes in two main forms. The first one is kinetic energy, and that is energy that is due to motion, and then potential energy, which can be due to an object's position or an object's deformation. So if you think about an object's position, it could be in a place where it could be struck by another object, so it houses this potential energy. Or if you think about playing kickball or dodgeball, the actual rubber balls or foam balls that you used when they hit someone or when you kicked the ball itself went from a circular shape to someone somewhat having a dent in it. So now this particular object contains potential energy based on this deformation of the material. So kinetic energy is defined as an object's capacity to do work because of its motion. And the mathematical equation for kinetic energy is Ke equals 1/2 mv squared, where in this formula kinetic energy is Ke, and the unit for this is actually Newton meters or joules, because it is kilograms times meters per second squared. Okay, so that's meters squared over second squared, which can then be converted to kilograms times meter per second squared times meter, which then equals a Newton meter, or more commonly known as a joule. All right. So then, of course, in our equation, m is equal to mass and v is equal to velocity. And as we've stated already, if you are given grams or even miles per hour in a particular problem, make sure that you are converting to kilogram and meters per second. So in our basic example for kinetic energy, how much kinetic energy in a 5-ounce baseball or 145 grams thrown at 80 miles per hour or 35.8 meters per second. All right, so if we do this mathematically, we know that Ke is equal to 1/2 mv squared. So Ke is going to be equal to 1/2 0.145 kilograms times 35.8 meters per second, and we're going to square that. And once we do this math, we will get kinetic energy is equal to 92.9 joules. Moving to potential energy, there are two forms of potential energy: gravitational PE and strain PE. Gravitational potential energy is the energy inherent due to an object's position relative to the Earth. So this is usually related to an object's weight or its height above the ground or some reference. Okay. So typically gravitational PE is simply referred to as potential energy, but in our class we will refer to it as gravitational potential energy. Now, strain potential energy is a type of potential energy that is typically referred to, especially in sport. So this type of energy is usually, or more simply, referred to as elastic potential energy, or most people shorten it to EPE. All right. Now, this can be relative to sport based on equipment. If you think about a pole vaulter, there is strain potential energy stored in the pole that is bent as they stick into the ground, and then it bends tremendously and then essentially flings them over some height. But it can also be relative to biological tissues like tendons, ligaments, and connective tissues. If you've had exercise physiology, or even it could be talked about in anatomy and physiology, the stretch shortening cycle. So if a muscle is stretched, it is actually storing that strain potential energy, or as I said, more commonly referred to as EPE, in the muscle, that is then going to provide a greater force once that muscle shortens and pulls on some segment. So gravitational potential energy is the energy due to position and is mathematically referred to as PE equals weight times height, all right? Or more commonly, PE is equal to mgh, where PE is potential energy, again measured in joules. Mg is mass times the acceleration due to gravity, or one's weight, okay, measured in newtons, and then the height above some reference point. Typically it's the ground or some other reference. So this will be measured in meters. What's really important to note in mathematically solving height is knowing your reference point, all right? If it's above the ground, it should be stated, but if it's above some other reference point, it will also be stated in the problem. So if we are asked how much potential energy is in a 100 kilogram bar held 70 centimeters above the starting point on a weightlifter's chest, and we know that 5 centimeters above the lifter's chest is our reference point, PE is going to be equal to 100 kilograms times 9.81 meters per second squared times 0.70 meters is going to be equal to 686.7 Newton meters or joules. In calculating strain energy, which is again the energy due to a deformation of an object, strain energy is equal to 1/2 K delta X squared, where SE is equal to the strain energy stored in the deformed object, which is measured in joules. K is the stiffness constant of a material, which you will be given within a certain problem set and is measured in Newton meters. And the change in X is equal to the deformation, or the change in length of the object from its original size. So if you were asked to calculate the strain energy stored in a tendon that is stretched 5 millimeters if the stiffness of the tendon is 10,000 Newton meters. So we know that strain energy is equal to 1/2 K delta X squared. So then SE would equal 1/2 10,000 Newton meters times 0.005 meters squared. Calculating that out, strain energy would be equal to 0.125 joules of this tendon. So next we're going to cover the work energy principle, which states that the net work done by all external forces acting on an object or a system of object causes a change in the mechanical energy of the object. Now, this is mathematically represented by FD is the total change in mechanical energy, where FD is equal to change in kinetic energy plus the change in potential energy, which can also be written as FD equals KEF minus KEI plus PEF minus PEI, where this is kinetic energy or final kinetic energy minus initial kinetic energy plus final potential energy minus initial potential energy is equal to the total net work done or total change in mechanical energy of a system. So let's look at this first example calculation for the work energy principle. In the ascent phase of the bench press, the lifter raised the 1,000 Newton bar 0.7 meters by doing 700 joules of work on the bar. The bar was at rest, so velocity is 0, kinetic energy is 0 at the start, which was 5 centimeters above the chest, and at the end of the lift, the bar was 75 centimeters above the chest. So the work of the lifter on the bar changes the total energy of the bar. So for our calculation, we know that FD is equal to the change in KE plus the change in PE. Alright, well, we know that KE is 0, okay, because it was at rest, okay, plus final PE minus initial PE. So FD is equal to final MGH minus initial MGH, because this is the formula for potential energy. So FD is ultimately equal to mass, or the weight of an object, times the final height minus the initial. So FD is equal to 1,000 newtons times 0.75 meters minus 0.05 meters, and FD is going to be equal to 700 joules. Now, the conservation of mechanical energy states that the total mechanical energy of an object stays constant if no external forces other than gravity act on the object. So, mathematically, this would look like initial kinetic energy plus initial potential energy plus initial strain energy is going to be equal to final kinetic energy plus final potential energy plus final strain energy, where K is kinetic, P is potential, SE is strain, and of course I and F are equal to the initial and final states of each of these. So if you think about an object that is rising up in the air, the kinetic energy is actually decreasing because, as we know, KE is equal to 1/2 mv squared. So V is going to approach 0. all right? So then your velocity is decreasing, therefore your kinetic energy is decreasing. However, your potential energy is increasing because we know that PE is equal to mgh. So if H goes up, then PE also goes up. So this is just a basic example of how the total energy of the system is going to remain constant as these different independent variables fluctuate. If the object were coming down, we would see relatively the same relationship, right? Kinetic energy is going to increase because velocity is going to go up, therefore K is going to go up. However, the height is decreasing, therefore potential energy is going to also decrease. But again, the total energy of the system remains constant because of this conservation of energy relationship. So moving to our next concept of power. Power is the rate of doing work. So mathematically, power is equal to U over delta T, all right, because it is a rate, you have to have time, where P is equal to average power, U is equal to work, or force times distance, and delta T is obviously equal to the time it takes to do that work. Now the units for power are going to end up being joules per second, which is also equal to a watt. So watt is going to be the units that we use for power. Now, alternatively, power can also be thought of as how quickly or slowly work is done, or power equals force times velocity. And the way that we look at this from a mathematical perspective is if average power is equal to work over the change in time, and we know that U is equal to force times distance, which would be over time, this can be rearranged to force times distance over change in time, or displacement over change in time, which is then going to be equal to average power is equal to the average force times average velocity. So power in biomechanics is often looked at relative to locomotion or some type of cyclical activity like walking, running, cycling, or swimming, because the ability of an athlete to increase displacement of an object or some body part while exerting some force directly affects performance of a lot of skills in sport. So we often look at the velocity of locomotion, which is equal to the cycle rate times the cycle length, where cycle rate is how often the motion is repeated per minute, and the cycle length is what distance is traveled per cycle. So to move faster or slower, a performer or an athlete can change the cycle rate, the cycle length, or both, but oftentimes we see that one of these variables is changed by some kind of injury or some type of even disease. All right, so this is how power is more directly applied to sport through biomechanics. Now, there are significant constraints to power with human performance, and that is because power output and endurance are actually inversely related, meaning if power goes up, endurance is going to go down, and vice versa. So high power output, meaning you are exerting a large force over a great distance, is sustainable for only a short duration, where low power output is sustainable for long duration. So if you think about a cross-country runner versus basketball or softball, baseball athletes, cross-country runners are going to exhibit low power output because they can sustain this output for extreme time lengths, right? But if you think about basketball, baseball, and softball athletes, they exert much higher power outputs because they're often incorporating sprinting rather than jogging or long distance running into their sport. But this is sustainable for only a short amount of time. So this graph is just a visual representation that maximal power output decreases with increased duration of the activity. And this relationship really shows the mechanical constraint that is placed on humans by their power generating system, or what is otherwise known as our metabolic system. So this is the end of our chapter 4, or the energy and power and work chapter. So please make sure you watch both parts of this chapter, and we will do our problem sets in class.